Welcome to Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do appreciate and see the beauty in the simpler problems. So today, we continue the MIT 2019 Integration B qualifying exams. We'll start with problem 11 all the way to problem 20. In the previous session, we covered problem 1 to 10, and I hope if you are interested, you would refer to our channel and get to see how we solve those problems. So today we're going to the next phase of problem 11 to 20. Now, before I go into the questions, I'd like to thank our subscribers. Thank you so much for just blessing us with your support and continuing to watch our videos. It's your support that motivates us to come here every day and do this work. For our first-time visitors, just a sneak peek into what we do here at Everyday Mathematics. We go around, look for very hard problems, and we come back here with some of the solutions that we think befit the problems. To our repeating visitors who haven't subscribed to our channel, we do encourage you to just take a moment and pause the video and subscribe to our channel. Your support is much needed. Thank you. And so let's go on to the problems. So problem 11 is here, problem 12, problem 13, problem 14, problem 15, problem 16, problem 17, problem 18, problem 19, and 20, right? So let's go to problem 11. Problem 11 is the integral from x equals to 0 to 2 pi of cosine x times cosine 2x times cosine 3x. So the identity that I would like to use is cosine A plus cosine B is equals to 2 cosine A plus B over 2 cosine A minus B over 2. So if we take these two functions, cosine 2x and cosine 3x, what that means is that we can express this product as a sum or as an addition format or formalism, such that cosine x times cosine 2x times cosine 3x is equal to the integral cosine x times cosine 5x plus cosine cosine x. Now, I have forgotten a half here, so there should be a 1 over 2 somewhere there. And so that we have 1 over 2 cosine 5x times cosine x plus cosine squared x. Okay, then we can use the same identity, and so we have for cosine 5x cosine x being equal to a half cosine x plus cosine 4x. And then the cosine x squared can be expressed as cosine 2x plus 1 over 2. And so if you look at this problem very carefully, from the interval 0 to 2 pi, cosine x will definitely have a positive negative oscillation that are equal in number. And that means that the area under the curve will essentially be 0. Same for cosine 4x and same for cosine 2x. And therefore, what we're really left with is this half times this half, which is the integral of a quarter in that region. And that means that quarter, taking quarter out, and we're left with 1. Integrating 1 will be x. 0 to 2 pi will be now 2 pi minus 0, which is 2 pi. 2 pi times a quarter is pi over 2. And this is our answer. Okay. Problem 12. Problem 12 is the limit as n tends to infinity from x equals to infinity to positive infinity of e to the power x to the power 2n. And this is a very interesting problem. What you'd want to do is separate this into 3 intervals. That is, from you integrate, before doing that, you could take this limit into the integral sign, and then you'd want to separate this into three intervals, from negative infinity to -1, and from -1 to +1, and from +1 to infinity. Now with this, when x is less than -1, and since we have a square here, this entire thing tends to 0. In the interval, this tends to 0 because this x value tends to a very large value, and so the entire number goes to 0. However, between -1 and 1, because as n tends to infinity, only the x to the power n part tends to 0, and so we're left with e to the power 0, and this here, the entire expression tends to 1. Here, the entire thing tends to 0. So essentially, you're left with the integral of 1 to from -1 to 1. And so what that means is you have x here, lower limit -1, upper limit 1. And so you're left with 2. So the graph of what is really happening here is that you will have -1, +1, and so all here will tend to 0. You have a rectangle like that, and this is 1. So the area here is what you're left to solve with. And so the answer is 2, because we have 2 times 1. Problem 13, integral from x equals to 0 to e of x to the power 1 over log x. Any number can be expressed as, if you have x, for example, that is the same as e to the power natural logarithm of x, right? So this one here now means that we are left, this will become e to the power log x to the power 1 over log x. And so using the rules of logarithm, this 1 over log x goes to this constant side. And so as you can see, this and that cancels out, and you're left with only e. And integrating e is a constant, and then x is what we get after integration. That we have 0 to e. So e minus 0 is e. E times e is equals to e squared. And this is the answer. Problem 14 is the integral from x equals to 0 to pi over 100 of sine 20x, sine 19x over cosine 20x plus cosine 19x. So here we use this identical cosine a plus cosine b is equals to 2 cosine a plus b cosine a minus b, and sine a plus sine b is equals to 2 sine a plus b over 2 cosine a minus b over 2. So looking at the numerator, what that results into is twice sine of 20x plus 19x over 2 times cosine 20x minus 19x over 2. So this becomes 39x over 2, 39x over 2. This is x over 2, x over 2. So this and that would cancel, and we're left with but these two also cancel. We are left with sine 39x over 2 over cosine 39x over 2, which is the same as 1 over 39 over 2 negative log of cosine 39 x over 2. Since the numerator is the negative derivative of the denominator. And so we have our limits here applied appropriately. Cosine of 39x, cosine of 39 over 2 times 0 is 1. Log of 1 is 0. So the only thing that remains effective here is the upper limit. And so substituting in the upper limit, we have -2 over 39, which is 1 over 39 over 2. Logarithm of cosine 39 over 2 times pi over 100. So this results into -2 over 39 log cosine 39 over 200 pi. And this is the answer. Problem 15, which is the indefinite integral of e to the power x cosine squared x plus e to the power x cosine cosine x sine x minus e to the power x sine squared x. So what I can do is I can bunch that with that, and so we are left with e to the power x into bracket cosine squared x minus sine x, and so that is the same as cosine 2x, right? And then this e cosine x sine x is the same as a half of e to the power x sine 2x. Now, what we know is that this cosine x is the same as a half the derivative of sine 2x. And so derivative of ex is derivative is ex. So we can express it like that. So what you see here is, looks like, since we have a half of sine 2x here, and we have a sine 2x here, and we have e to the power x, e to the power x here, this just looks like the derivative of a product of e to the power x and a half sine 2x. And so since we have that, when we integrate, the answer is a half e to the power x sine 2x plus the integration constant. Problem 16 is the integral from x equals to 0 to pi over 2 of sine x over sine x plus pi over 4. What I'll do is I'll expand sine x plus pi over 4 into sine x cosine pi over 4 plus cosine x sine pi over 4. This is 1 over root 2, and this is 1 over root 2. Okay, pull it out, it becomes the square root of 2 times whatever is here, as we can see here. And so we have square root of 2, the integral from x equals 0 to pi over 2 of sine x over sine x plus cosine x. This is a very interesting problem, because if we also let x be equal to pi over 2 minus u dx is equal to negative du, and so this becomes cosine u, this becomes cosine u, and this becomes sine u. The limits flip, but because of the negative sign, it flips back. So essentially, this here is the same as the same integral, but x and sine x are flipped. So in other words, if we let I be equal to the square root of 2, integral of 0 to pi over 2 sine x plus cosine x, then 2i is the same integral from 0 to pi over 2 sine x plus cosine x plus 2, plus an integral where we flipped x and sine x. So we have here cosine x plus sine x. And so when you add them, 2i is the same as twice the 2 times root 2 of the integral, because the numerator now becomes equal to the denominator. It cancels out and we're left with 1. So this is the same as the integral of 1, and since which is x, and then pi over 2 minus 0 becomes pi over 2. Pi over 2 times 2 root 2, we have root 2 root 2 pi. And since we have this 2 here, I becomes root 2 over 2 pi. That's the answer. Okay. Problem 17, the integral of dx over x plus cube root of 3 of x. Let u be equal to cube root of x, and therefore u to the power 3 is equal to x, therefore 3u squared du dx equals to 1, therefore 3u squared du is equals to dx. And so in place of dx, we have 3u squared, and in place of x, we have u cubed, and this becomes u. So this and that goes, so we are left with u over u squared plus 1 times 3 outside here. And so one thing we could do is, we see that this is the natural logarithm, because essentially the numerator is half the derivative of the denominator. So we have 3 over 2 natural logarithm of u squared plus 1 as our integral. Now we replace u with x, and that becomes 3 over 2 natural logarithm of u to the power 2 over 3 plus 1 plus the integration constant. Problem 18, which is the integral from x equals to 0 to 2 of x to the power x squared plus 1 times the twice natural logarithm of x plus 1. One thing you could do is you can separate this a little bit. So we have x to the power x squared times x here times 2 log x plus 1. And as you can see, this can also be expressed as e to the power log x to the power x squared. And then we multiply x across, so we have 2x log x plus 1. And what we see here essentially is we have e to the power x squared log x times 2x log x plus 1. And so this here is the same as the derivative of this power here, right? And that means that because if we see here, x squared times 1 over x is the same as the derivative of log x times x squared. So one thing we could do is now go ahead and really see that what we're seeing here is the derivative of the product of, not even the product, is the derivative of e to the power x squared log x. So that is what we have here. And so the answer is e to the power x squared log x plus c. If you want to express it in a more succinct way, if you take this x up here, this becomes x to the power x squared plus c as our final answer. Problem 19, which is the integral of 2x cubed minus 1 over x times x cubed plus 1. One thing you could do is we have x here, but then we can express this as partial fraction, which will become 3x squared over x cubed plus 1 minus 1 over x. And as this here, this is the derivative of the denominator here. And this is also the derivative of the denominator here. So we get log x cubed plus 1 minus log x. I mean, you could spend some time to really confirm that this boils down to this. It's a very trivial problem. You could just do it like this. 2x squared minus 1 over x, x cubed plus 1 is equivalent to a over x plus b x squared plus cx plus d over x cubed plus 1. And you begin just when you multiply this across and you set x to 0, so and slowly you can begin to derive the value of the constant of a, b, c, and d, and you should find these constants all. Problem 20, so the harder one, cosine of arctangent x integral. So what here we do is we can say let u be equal to arctan of x such that tan u is equals to x. So sec squared x, sec squared u du dx equals to 1. Sec squared u du is equals to dx. Therefore, this becomes cosine u, here this being u, and then dx being sec u du. And so since sec squared u is 1 over cosine squared u, one of these cosine u cancels out with this, so we're left with sec u. And so we have 1 over cosine u as our problem, which is cosine squared u over 2 minus sine squared u over 2, right? And so we can split this such that it is cosine u over 2 plus sine u over 2 times cosine u over 2 minus sine u over 2. Now we can create this, we can actually separate this into partial fractions in a way that this here is the same as cosine u over 2 plus sine u over 2 over cosine u minus sine u over 2 plus cosine u minus sine over 2 over cosine u plus sine u over 2. And it's easy to prove that. So this, the numerator here is the same as the derivative of the denominator, negative. And this here is the same as the derivative of the denominator. So essentially we have natural logarithm of cosine u plus sine u over 2 minus natural logarithm of cosine u over 2 minus sine u over 2, and then plus the integration constant. So if this is our number, we can now use the rules of logarithm to make a fraction out of it, cosine u over 2 plus sine u over 2 over cosine u over 2 minus sine over 2 natural logarithm plus c. And then we could multiply the numerator and denominator with cosine u over 2 minus sine u over 2. Such that we have natural logarithm of cosine squared u over 2 minus sine squared over 2 for the numerator, and cosine squared u over 2 plus cosine squared u over 2 minus twice sine u cosine u. And what that means is that we have cosine u here over 1 minus sine u plus c. So the interesting thing is, well, we saw that let u be equal to arctangent of x. And so if we have a right angle triangle with the base angle being u, therefore, since x is tangent of u, we'd have x over 1 be equal to the tangent. So opposite will be x, adjacent will be 1, and the hypotenuse will be 1 over x squared. And sine u is the same as x over the hypotenuse is 1 square root of 1 squared. Cosine u is the same as base over the hypotenuse, which is 1 over square root of 1 plus x squared. So in place of cosine u and sine u, we replace with this x formulas because we have to go back from the u world to the x world. And so we have natural logarithm of 1 over square root of 1 plus x squared for this, and minus over 1 minus x x over square root of 1 plus x squared in place of sine u. So multiply both sides, the numerator and denominator, with root of 1 plus x squared. Changes things. And we can reorganize it a little bit so that when you do that, this and that would go. And then if you multiply by square root of 1 plus x squared plus 1 to the denominator and the numerator respectively, this becomes natural logarithm of square root of 1 plus x squared plus x. Denominator becomes 1 plus x squared minus x squared. So this x squared cancels. So the answer literally becomes the natural logarithm of square root of 1 plus x squared plus x plus the integration constant. So this is the end of our problem solving today. Thank you so much for paying attention to our proposed solution. If you're not subscribed, please endeavor to subscribe to our channel. We will really use your support. It's been an absolute pleasure. If you have any comment and you want to seek clarification for a step or the other, please don't hesitate to leave a comment on our comment section. Thank you so much. Until next time, à tout à l'heure, à la prochaine fois.